Remember in Calc 1 we approximated the values of a function near a point A using linear approximation. And of course the graph of this linear approximation was just the graph of the tangent line to the curve at the point A. So we actually had an algebraic formula for this tangent. It was y equals f of a plus f prime of a times x minus a, and the values of f of x stayed pretty close to the tangent for values of x near a. If we have infinitely many derivatives at a, and suppose f of x equals the sum of its Taylor series in some interval around a, then we know that the partial sums get closer and closer to the values of f of x for x values near a. So we can get a good approximation to the values of f of x by taking the nth partial sum of the Taylor series when x is near a. So the nth Taylor polynomial is given by the sum of the first n plus 1 terms of the Taylor series. It ends at the term, the nth derivative at a over n factorial times x minus a to the n. And this is a good polynomial approximation to f of x for values of x near a. Furthermore, it has the property that Tn of a equals f of a, and also the ith derivative of this Taylor polynomial at a matches the ith derivative at a for I values between 1 and n. And notice that this is a generalization of linear approximation. If I take n equals 1, then the first Taylor polynomial is actually the linear approximation we studied in Calculus 1. Here are some pictures. Here we have the graph of y equals e to the x shown in red, and the graphs of some of the Taylor polynomials shown in blue. On the left we have the graph of the fourth degree Taylor polynomial at 0. In other words, the fourth degree Maclaurin polynomial for e to the x. And we see that its graph is a pretty good match for the graph of e to the x for values of x between minus 2 and 2. And on the right we have the 10th degree Taylor polynomial, and now we see that this is a pretty good match for the graph for values of x between minus 4 and 4, or even minus 5 to 5. The moral of the story is the larger the degree of the Taylor polynomial we take, the smaller the error of approximation is going to be for values of x near a. And also the interval around a for which the approximation is good expands as the value of n increases. So we knew from before, from the last section, if f of x does actually sum to its Taylor series about a, or for values of x near a, then the limit as n goes to infinity of the Taylor polynomial evaluated at x has to be f of x. And of course, as we mentioned when looking at the graphs, larger values of n should give me a better approximation to f of x. So when approximating, we can use Taylor's inequality to help control the error in our approximation. And the error in our approximation is given by the absolute value of Rnx, which is the absolute value of f of x minus Tnx. We have two ways to estimate this error. We can use Taylor's inequality. We know that if we have an upper bound for the n plus 1th derivative of f on a particular interval around a, then we know that the absolute value of the remainder is less than or equal to that bound times the absolute value of x minus a to the n plus 1 over n plus 1 factorial. And also, if our Taylor series is an alternating series, we can always use the alternating series estimate for the error, or the upper bound for the error, being the absolute value of the n plus 1th term. We've looked at a few examples in Mathematica where we judged that we had a pretty good approximation with a polynomial by looking at the graph of the function. However, we don't always have access to the graph of the function, and judging by the graph is not a very precise way to control the error. So these algebraic methods, although they look a little more complicated, if you master them, they give you better control over your error of approximation.